Hello everybody, and welcome to another video. In this video, I will be covering related rates, which is an incredibly useful tool from calculus, which is applied in many real-world examples and helps us gain more of an intuition about how calculus functions in the world around us. In this problem, we have a piece of hail hitting the surface of a body of water, leading to a circular ripple, as you can see in this demonstration below. So this circle has a radius of r, which is increasing. Now the rate of change of this increasing is 0.5 meters per second. So every second, this radius is increasing by another 0.5 meters. So what this means is that dr over dt, so the rate of change of this radius is equal to 0.5 meters per second. Now, the question is asking how fast the area of the circle is increasing when the radius of the ripple is 2 meters. So what this question is asking for is dA over dt, where A is the area, at r equals 2, or when this radius right here is 2 meters. So to get started, let's look at the equation for the area of a circle, where we have A equals pi times the radius squared. Now, we want to differentiate both sides with respect to time, as this will give us, on the left side, our equation for the derivative of area with respect to time. Now, when we do this to the right side, we get d over dt of pi times r squared. Since this pi is a multiplicative constant, we could just take it to the outside of this right here, and we get the derivative of r squared with respect to time. For this problem, we are going to be using implicit differentiation as well as chain rule. So our outside function in this case is going to be the squared part, and our inside function is going to be just r. So our chain rule tells us that this is going to be 2 times r, as that is a derivative of the outside when you keep the inside the same, times the derivative of the inside, which is dr over dt. Now this is all multiplied by pi, and this is equal to the derivative of our area with respect to time. Now this equation that we have right here is generalized for all existing circles that have a radius which is increasing, or even not increasing. This just works for all circles. This is always true, that the derivative of area with respect to time is equal to 2 times pi times r times the derivative of the radius with respect to time. As if this was 0 and the radius wasn't increasing, then this would be 0, but the change in area would also be 0 since this isn't changing at all. Now this equation right here is set in stone. So for this problem, we know that dr over dt is just 0.5 meters per second. So we can plug that in to our equation for the derivative of area with respect to time, where we get that this is equal to 2 times pi times the radius times 0.5 meters per second. Now the 2 and the 0.5 cancel each other out, so you are just left with pi, which has units of meters per second, times your radius is equal to the derivative of the area with respect to time. Now, it is asking for this area at the point r is equal to 2. So we could just plug in r equals 2 for our radius for this problem. So we have that this is equal to pi meters per second, or we don't need this right here, then that actually needs to be on the outside, times 2 meters, and this is at 2 for our value r. So this is equal to, we know that dA over dt when r equals 2 is equal to 2 pi meters times meters per second which is equal to 2 pi meters squared per second. So what this is saying is that the rate of change of the area with respect to time is equal to 2 pi times area per second. I hope you all enjoyed this video and found it interesting and useful, as this is one of the coolest parts of calculus. I say that about a lot, but this is genuinely a very interesting class. I hope you enjoyed. Please like and subscribe, and thank you for watching.